Hi, welcome to our video about liquidity extraction in chemical engineering and its applications. Firstly, let me introduce about separation process in chemical engineering. Separation process are techniques used in chemical engineering to separate different components in a mixture. These processes are crucial in chemical engineering as they allow for the purification of products, recovery of valuable materials, and also efficiency management of resources in various industries. There are a few separation processes such as filtration is for solid and liquid, distillation is for the separation process based on different boiling points, while liquid-liquid extraction is preferred when the substances are heat sensitive, the components in the mixture have similar boiling points, separation is based on solubility and not boiling point, and when two fluids are immiscible, and also when the separation by distillation is difficult or ineffective.
As shown in the diagram, the two phases, which are immiscible to each other, are brought into contact with a high degree of turbulence. This turbulence is essential to obtain high transfer units, effectively forcing the solute to move from the feed into the solvent. In solvent extraction, the density difference is taken into account to allow these phases to settle into distinct layers once the mixing stops. After this contact, they must be separated to ensure the purity of both the extract, the solvent now containing the desired solute, and the raffinate, the residual liquid that remains. I will explain one of the equipment used for the single stage extraction, which is the mixer settler extraction unit. I will explain. The process begins with the physical blending of the two immiscible liquid. Firstly, the light phase and the heavy phase will enter at the bottom. Next is the motor-driven impeller will aggressively agitate the liquid, which will create a fine emulsion that consists of the mixture of tiny droplets. The goal for this mixing is to maximize the surface area of the liquid to allow the solute to transfer from one phase to another liquid phase via molecular diffusions, and it also based on the solute solubility to the solvent. The phase where the extracted solute is concentrated is called the extract, and the residual liquid is called the raffinate. For this, once the chemical transfer has occurred, the emulsion will flow over a wheel into the large clarifying chamber. Because of the liquid has different density and are immiscible to each other, they will naturally begin to unstack. For the discharge and the collection, the top layer will flow over the top wheel into the collection chamber at the top right, while for the heavy phase liquid, the liquid will flow under the baffle to prevent contamination with the light liquid and into the heavy exhaust tube.
Okay, next, let me explain about centrifugal extraction. Centrifugal extraction is a high-speed industrial process that uses a rotating drum to rapidly mix two immiscible liquid such as water and oil, and then quickly separate them based on their density driven by intense of centrifugal force instead of gravity. Okay, first for the feed in centrifugal extraction is two immiscible liquid such as water and organic solvent are introduced into the extractor through the separate inlet. Second, the next is intense mixing, which the liquid enter the mixing zone, often in an annular space around the rotor or in dedicated chamber. Here, high shear and turbulence are generated, which promote rapid mass transfer of the solute between two phases. After mixing, the process moves into centrifugal separation. The mixed liquids are drawn into the spinning rotor. Centrifugal force act on them driving the heavier phase outward while the lighter phase remains closer to the center. Finally, we reach at the phase discharge. The separated phases exist through their respective outlet. The phase that has absorbed the solute is called extract, while the depleted original phase is known as terminate. This entire whole process about the centrifugal process, which is introduction of feed, mixing, separation, and discharge, happens continuously, efficiently within a single compact unit, making centrifugal extraction both fast and effective. Let's move with the next part is partition coefficient or distribution coefficient. First, imagine we have two immiscible solvents like a water and octane. When a solute is added, it distributes itself between two phases based on its solubility. At first, the solute might be more concentrated in water, but over time, molecules move from high concentration phase to the low concentration one until equilibrium reach. Just at equilibrium, the solute is more abundant in solvent where it dissolves better. This behavior is captured by the distribution coefficient, which is defined K. So the distribution coefficient actually is we want to measure how the substance divided between two immiscible liquid phases at equilibrium, which it represents the ratio of its concentration in those phases. So the value of K is molarity of organic phases divided with a molarity of aqueous phases. For example, the organic phases is a octane, the molarity of octane, and divided with a molarity of aqueous, which is water phases. So next, we talk about the application. First, in solvent extraction, the value of K tells us how efficiently a solute can be pulled from water into the organic solvent. Second is in chromatography is affect or influence the retention time of analyte. And third is the environmental science, which is we use to describe how the pollution and the partition between the soil, sediment, and water. Which is we want to determine the causes of the pollution occur.
Moving on to multiple stage LE, it consists of two or more extraction stages compared to single stage LE, where the raffinate from one stage contacts with fresh solvent in the next stage, and each stage reaches its own mass transfer equilibrium, and it can be arranged as cross-current or counter-current flow. The key features of multi-stage LE includes much higher overall extraction efficiency, uses solvent more efficiently, and enables high solute recovery and purity compared to single-stage LE, common in industrial separation, such as hydrometallurgy and also petrochemicals. So next, moving on, I'm going to explain about why multiple stages improve separation efficiency. So the first reason is fresh concentration driving fast in each stage. So basically, after one stage, the raffinate still contains solute. Contacting it again with fresh solvent restores a high driving force due to the difference in concentration gradient, and this causes more solute transfers at each stage. It is better than single stage is because single stage loses driving force quickly as equilibrium is reached. And next, for the second reason, it is due to the reason that each stage reaches its own equilibrium, but one equilibrium stage cannot remove all the solute. However, multiple equilibrium stages approach the theoretical maximum separation. So this is why we prefer multiple stages LLE compared to single stage LLE. And the last reason why we choose multiple stages LLE rather than single stage LLEs is because of the exponential reduction of solute concentration. In multiple stage LLE, each stage removes a fraction of the remaining solute. The remaining solute concentration, it decreases multiplicatively, not linearly. So this leads to a much higher overall recovery of the separation. So as I have mentioned in the previous slide, multiple stage LLE consists of two types, which is cross current and also counter current extraction. So let's focus on the co-current first. In the first stage, it consists of feed and also fresh solvent. And the second stage, and for the third stage and so on, it consists of raffinate and also the fresh solvent. So for co-current, each stage uses unused solvent, which lower the overall efficiency than counter current because it requires more solvent for the same separation. So in comparison, we have counter current extraction, which the fresh solvent contacts the most depleted raffinate, and solvent becomes progressively richer as it moves toward to the fresh feed, and the feed meets the richer solvent at the final stage. These provide a best solvent utilization, highest extraction efficiency, and it can achieve high recovery with less solvent.
Now let's look at the visual difference between single stage and multiple stage extraction. On the left, you see single stage extraction, just one contact between the feed and the solvent. Because they meet only once, there's limited solute transfer, and that means lower extraction efficiency. On the right, you see multiple stage extraction. Here we have multiple equilibrium contacts between the liquid streams. In counter-current system, the fresh solvent meets solute-rich feed, maintaining a high driving force for mass transfer. This leads to much higher separation efficiency. To make this idea concrete, let's walk through a simple numerical example. Imagine you are extracting acetic acid from water using isopropyl ether. You have 100 kilograms of water solution containing 20% acetic acid. In a single stage extraction, let's say 40% of the acetic acid transfer into the ether. So how much acid remains in the water after one stage? And what if you use two stages, each still removing 40% of the acid present at the start of the stage? Let's calculate and compare. First, the single stage calculation. We start with 100 kilograms of solution at 20% acetic acid. That gives us 20 kilograms of acid. In one stage, we remove 40% of that, so 40% of 20 kilogram is 8 kilograms removed, and that leaves 12 kilograms still in the water. The remove efficiency is just 8 divided by 20 times 100%, so that's 40%. So after one stage, more than half of the acid is still there. Now let's split the same process into two stages. The stage 1 is the same. We remove 8 kilograms, leaving 12. But now in stage 2, we remove 40% of what's left. So that is 40% of 12 kilograms, which is 4.8 kilograms. After the stage 2, only 7.2 kilograms of acid remain. In total, we remove 8 plus 4.8, which is 12.8 kilograms. That is 12.8 out of the original 20, which gives us a 64
That's
removal
all for our
efficiency.
video about liquid
By
extraction
just
in
adding a
chemical
second
engineering
stage,
and its
we have
applications.
significantly
Thank
boosted
you for
our
watching.
recovery. So to summarize, single stage efficiency was 40%, the two-stage efficiency jumps to 64%, and that is 24% more acid recovered. The takeaway is clear: more stages mean higher efficiency. But it is not just add more stages forever, because each new stage also adds cost, equipment, and complexity. In practice, chemical engineers balance recovery targets with economic feasibility, often choosing an optimal number of stages where the benefit outweighs the cost.
So here are some real industrial applications of liquid extraction. Firstly, it is pharmaceutical industries. Liquid-liquid extraction can be used to reduce the level of impurities and thus enhance the safety of the pharmaceutical products or medicine. Second, it can be used in environmental applications for the removal of contaminants in wastewater and also extraction of pollutants from industrial waste. Last, it also can be used in food industries, such as for the extraction of vegetable oils from seeds like soybean and sunflower. It also can be used for the decaffeination of coffee and tea. The advantages of liquid-liquid extractions are it can be used to separate different substances with similar boiling points. It can work for heat-sensitive materials, and it also can be more efficient than distillation in some cases. While for the limitations, it requires large amount of solvents, and the solvent disposal can be an environmental concern if we do not manage it well. And sometimes it is time-consuming and can be slower than other methods. In conclusion, liquid-liquid extraction is an important separation process in chemical engineering. It works by separating substance based on solubility in two immiscible liquids. Single-stage LLE is simple and it is suitable for basic separations, while multi-stage LLE offers higher efficiency and it is preferred in industrial process. The counter-current extraction is more efficient than cross-current extraction because the solvent is used more effectively.